today we are going to work again with differential equations, and we are going to introduce the regular problem of Sturm-Liouville that is going to be very related with the analysis of Fourier. So, and what is this going to be about? Well, the problem of Sturm-Liouville is going to be about solving a particular differential equation with some particular conditions. Okay, so first we're going to define that the problem of Sturm-Liouville is defined in a closed interval a comma b, where we are going to define two functions that are going to be, let's say, r of x and p of x, that in this interval are going to be greater than 0, and we are going to define also a function q of x, where r, p, and x are real valued functions defined in this interval. Okay, perfect. So after saying this, also there is another fact that r prime of x is going to be a real valued function defined in this interval. But the important thing here is to define the differential equation related to the regular problem of Sturm-Liouville, which is going to be the derivative with respect to x of r, let's say r of x, y prime plus q of x plus lambda, and then p of x times y equals to 0. Okay, so the first thing here to notice that is important is that this is a homogeneous differential equation, and it's a linear equation. Okay, also recall here that we have a parameter lambda that is going to be related with the eigenvalues corresponding to this differential equation, and with some eigenfunctions that are actually going to be the solutions of the differential equation. So that is going to be important. Okay, perfect. So we need to establish what are the conditions that the problem of Sturm-Liouville needs to satisfy. So those conditions are going to be that a1 y of a plus a2 y prime of a is equal to 0, and that b1 y of b plus b2 y prime of b is equal to 0. So recall here that the function and its derivative evaluated at one point, if we take a linear combination of this, we need to get 0. Okay, so that means that the function and its derivative are linearly independent. Okay, perfect. So again, the problem of Sturm-Liouville needs to satisfy these two conditions necessarily. Okay, so what we are going to show now is that if we have any functions that satisfy this differential equation, well, these two functions are going to be orthogonal functions with respect to px. So what does that mean? Well, that means that if we take the inner product from a to b of y, let's say yn of x, ym of x, we still need to multiply by p of x to get that this is going to be equal to 0 if m is different from n. Okay, this is the orthogonality condition, but with respect to the function p. Okay, so it is important because to guarantee orthogonality, we need to add this function into the inner product. So we are going to show that. First of all, we are going to say that yn and ym are solutions of the Sturm-Liouville problem. Okay, so that means that the derivative with respect to x of ryn prime plus q plus lambda n p yn is equal to 0, and that also means that the derivative with respect to x of rym prime plus q plus lambda m p ym is equal to 0. So what we need to do is to construct the inner product that I mentioned here to see what we get, and you will see that that will be 0 if m is different from n. Perfect. So what we are going to do first is to multiply the first equation by ym, and then the second equation by yn. And if we do that, we are going to get the next ym, and then times all these thing that I have here, like this, and equal to 0, and then yn times all these things. Okay, perfect. So with this, we have the two equations with the two functions involved. So what we are going to do is to subtract these equations. You see that for this piece, we will get ym, the derivative with respect to x of ryn prime, minus yn, the derivative with respect to x of ryn prime. And then here, looking that we have the same element q, yn, ym, and here q, ym, yn, we can cancel this q. And then we have a common factor p, yn, ym, here and here. So we will get that this is lambda n minus lambda m yn equals to 0. And we are going to take this piece into the right hand side of the equation to get, let me copy this, and this will be equal to yn that multiplies lambda m minus lambda n. I just switched the order of this subtraction. Perfect. So you can easily see, and I think I forgot a p here, of course. So you can easily see that if we take the integral from a to b with respect to x, here we are going to construct that inner product that we desire. This one that I just wrote recently. So that means that we need to take that integral on both sides of the equation. So from this, we are going to get that the integral from a to b of ym, the derivative with respect to x of ryn prime dx, plus the integral, actually minus, right? The integral from a to b of yn, the derivative with respect to x of ryn prime dx, is going to be, well, it will be lambda m minus lambda n, and then times the integral from a to b p yn dx, which is again the inner product that we wanted. Okay, perfect. So we are going to be interested in calculating what are these two quantities that we have here. And you can easily see that, well, looking that we have a derivative here and here, we are motivated to use the integration by parts method. So of course, that means that this part is going to be identified as a dB and this as u, so as this. Perfect. So what are we going to get? From this first integral, we will get u, which is ym, times b, that looking that we have the integral with respect to x of a derivative with respect to x, we will only get what is inside the derivative, that is rym prime from a to b, and then minus the integral from a to b of it will be b, which is rym prime, times du, which is ym prime dx. Okay, and then we will have minus u times b yn rym prime from a to b, and then a minus, but with this minus is going to be a plus, the integral from a to b of the rym elements, and then yn prime dx. Okay, perfect. So yeah, we can easily see that this element is the same as this, so they cancel. And what are we going to get? Well, we need to take the evaluation of the limits, and looking that, well, these three are functions of x, remember. So this will be ymb, r of b, yn prime of b minus ym of a r of a yn prime of a, like this. And then we will get minus yn of b r of b ym prime of b, and then minus, but with the minus of the fundamental theorem of calculus we will get a plus. So yn a r of a ym prime of a. So remember that we had that the condition that the Sturm-Liouville problem needs to satisfy is that a linear combination of the derivative and the regular function needs to be equal to 0. Okay, so do we have something like this in our expression? Well, actually yes. As you can see here, we have the derivative of y evaluated at a and the function y evaluated at a. And of course, looking that these are real valued functions evaluated at a, this represents a constant number. Yeah. So that happens again in this case because, well, we are evaluating the functions at a. So we have a constant times the derivative evaluated at a and a constant times the function evaluated at a. And you can easily see that that same thing happens here, but we can see it with the function evaluated at b and the derivative of the function evaluated at b. So the thing here is that we are going to get something of the form a1 y n a plus a2 yn prime of a, and then plus b1 yn of b plus b2 yn prime of b. And looking that we need to satisfy the conditions from the Sturm-Liouville problem, of course this is equal to 0 plus 0, which is 0. Perfect. So that means that this quantity that we have here, well, it's equal to 0. So that means that the integral from a to b of yn ym p of x dx is equal to 0. That is going to be known as the orthogonality condition for the Sturm-Liouville problem. Remember that we had that this integral was multiplying a factor of lambda n minus lambda m. So it is important because this means that when m is different from n, well, we will get that this quantity needs to be different from 0. So there is no other way to have the integral that we are interested in to be equal to 0. Okay, so that's why it is important to recall that m is different from n, just to make this different to be different from 0. Perfect. So that is how we show that two solutions for the Sturm-Liouville problem are orthogonal. Okay, so before finishing this lesson, let me write a quick example, a very easy example of a Sturm-Liouville regular problem. That is going to be y double prime plus lambda y equals to 0. You know, this is a very easy differential equation, but and actually very well known, that is going to be of the form of the regular problem of Sturm-Liouville. And why is that? Because you can rewrite this equation as the derivative with respect to x of, let's say, 1 times y prime, and then plus 0 plus lambda times 1 times y equals to 0. And if you look to this, we can easily identify that this one is equal to r, this 0 is equal to q, and this 1 is equal to p of x. So that means that this equation has that same structure. Perfect. So And again, well, we need to specify what are the conditions that needs to satisfy this differential equation to be as the Sturm-Liouville problem. And that condition will be maybe that y of 1 plus y prime of 1 is equal to 0. And we can also say that y of 0 plus y prime of 0 is equal to 0. In this case, we can see that we are defining the problem in the interval 0, 1. Okay, perfect. So with this, we have defined an example of the Sturm-Liouville problem. And just remember that the solution for this problem is of the form, well, it will depend on the value of lambda, but if lambda is greater than 0, you know that the solution for this is of the form y equals a times cosine of the square root of lambda x plus b sine the square root of lambda x. And in the exponential form, we will get that y is equal to a e to the I square root of lambda x plus b e to the negative I the square root of lambda x. And in the case where lambda is less than 0, well, we will get that the solution is of the form y equals to a e to the square root of lambda x plus b e to the negative square root of lambda x. Okay, perfect. Just to give you the solution of this example of the Sturm-Liouville problem. Okay, perfect. So I think this is a good moment to finish the lesson. And yeah, let's just recall, this was a very quick introduction to what the Sturm-Liouville problem is about.